start now. So hello everyone, and welcome to the third edition of PyData Helsinki Meetup. Today we've got two speakers in two different topics with a sort of common theme. First, we have Sara Tähtinen, data scientist at Tile Studios. She would be speaking about explainable AI, proposing alternative methods beyond those popular ones like SHAP or LIME that are restricted to just a post-prediction, post-model predictions. And then the second topic is in NLP. For that, we have Aapo Tanskanen, data scientist at Gofore. He will be presenting zero-shot text classification, which is useful when you don't have labeled data available, and that without the need for GPT-3. So here we've got some alternative methods for both NLP and explainable AI. So the way this meetup will go is we will start with a brief introduction, and then we'll have the first talk from Sara Tähtinen about explainable AI, alternative methods, then a session of Q&A, and then the second talk from Aapo Tanskanen about zero-shot text classification without GPT-3, and then another session of Q&A. So, what is PyData Helsinki? PyData Helsinki is first a community for users and developers in data analysis, data science, and machine learning to share ideas and learn from each other. But it's also a series of meetup. For now, we are organizing a meetup each month on the last Thursday of each month. And for now, we have three organizers, Ali Eladi, Hunain Derar, and Sari Butaghat. So we are always looking for speakers, but also sponsors. And if you have any question or want to take part in the next PyData Helsinki meetups, please reach out to us through our email, pydatahelsinki@gmail.com. Follow us on Twitter, PyData Helsinki, and also at meetup.com/PyData Helsinki. You can also reach out to any of the organizers. And a quick reminder of our code of conduct. Please be kind, no insults or harassment or discriminatory language appropriate. So that's it. Without further ado, Sara, the floor is yours. So you can share your screen now.
Right. Sorry, someone. Here. You should be seeing the slides now, right?
Yes, we do.
Great. So the first topic is about explainable AI. So the outline of this talk is that I will first give an introduction to the topic. So in this talk, I will be going through explainable AI methods for images and deep learning. First, I will go through pixel-based explanations, so LIME and SHAP, and then I proceed to the gradient-based heat maps like Grad-CAM and so forth. Then I will also go through pre-modeling explainability, so how to look into your training data. And then at the end, I will go through a few alternative methods for explainability. First, I want to say about this terminology that I will be using in this talk. So sometimes this topic is divided into three different categories. And these categories are meant to explain, interpret, and understand AI. In this talk, I will refer all of these categories as explainable AI or xAI. Just because there is a lot of debate that what methods are actually interpreting the AI and which ones are explained and so forth. So I would use only one term to make matters simple. So about myself, I'm Sara Tähtinen, and I have a research background. So I have a PhD from theoretical particle physics. Previously, I worked as a machine learning developer in computer vision and deep learning. And now I'm in a project, Explainable AI project in my current job at Dane Studios. And we are part of this AIGA consortium that is a project that is partly funded by Business Finland. And in this project, I act as an xAI researcher. So I go through papers and then suggest different explainability methods that we could try out and then also test these models. But I can't, unfortunately, reveal that what methods we are looking into or share any of our results. So let's start by a brief intro to the topic. First, I will briefly explain the deep learning because I know that not everybody here is a data scientist. So let's think about the simple case. In the simple case, we have a large image set, and in these images, we have also the class labels. So for example, there is image of a cat, and then the label says that a cat. Then we also have a complex model called neural network. And in this network, we have millions of tunable, or often millions of tunable parameters. These are organized in layers that are connected with weights. And if you kind of think that what means the training phase, you can kind of like say that you try to fit the data into a very complex model. So what happens when you use it? You have an image. You give this image to a black box, which is your model. But because the model is so complex, you don't really know how the parameters are connected with each other, or you can't understand how they are connected. There is nothing mysterious going on, but it's just so complex that humans can't understand these complex models. So then the black box just outputs a result. Sometimes the result makes sense, sometimes it doesn't. This is completely like I just made up this example, but very often, as I've used these images, very often the predictions doesn't make any sense. And there is no way to know that what actually happened. So there is this increasing demand to somehow explain that what the model did and why it predicted the output it did. But there is this problem. If you want very accurate results, you need to use complex models. So the more complex your model is, the more accurate it is, but the more difficult it is to explain. So if you think about a simple case where you have data points and you fit a line to the points, then your output changes. It's easy to explain that now the prediction is here because it simply follows the line. But with neural networks, when you have millions of parameters that affect to the results, it's really difficult to give any kind of explanation why the outcome was what it was. So even though the explainable AI methods try to summarize what goes on in the method, it will always lack some certain details. So remember that the deep learning models are very complex and the explainable AI is able to summarize only a small part of it. So it will never explain them fully. But sometimes that is enough that we understand a little bit more. Then these explainability methods are directly linked into data ethics, because if you can't understand what your model is doing, how do you know it's fair? There is these typical AI blunders from the previous years. So, for example, Google that identified Black people as gorillas, and then Zoom with virtual backgrounds that made some people that were very Black or very white to lose their heads. Then there was this Amazon Carry service that recommends mostly males, and the reason was that majority of the workers were males. So the model learned that women are not good fit for this purpose. So if a good candidates were simply ruled out because in their CV it read like women or women's basketball team captain. And that's why it ranked only males too high in this career service. And then there was this case that, for example, healthcare algorithm in USA that failed to flag serious illnesses on Black people. The reason for that was that white people have better healthcare, so they are diagnosed more probably. So when the algorithm was asked to find serious illnesses on the patients, it preferred white patients over Black patients simply because the data was biased. But it's important to remember that it depends what kind of questions you want the explainable AI to answer. It depends a lot that what kind of role you have in this process. So, for example, data scientists, so you can kind of divide this target audience of explainable AI into 5 different groups. The first group is data scientists and developers, and they want ways how to improve the model, train more efficiently, and validate the results. Then there are domain users, so for example, doctors and bankers and so forth, that are in their work using this AI. And there it's important that they trust the decisions made by AI, but they also need to understand what it's doing. Then it's also important to know the problematic cases so that they can look deeply into those cases. Then there is these regulatory entities and lawmakers that need to make sure that the models are fair and that the model works as promised. They need to also understand the idea behind the system and evaluate if that's appropriate. Then there is also managers and decision makers that need to understand the application, its limitations, and their potential value. And then there is the last group, which is users. The users, the most important thing in this group is that the users have right to know knowledge on decisions affecting them. There is this famous GDPR rule that if you actually apply it very strongly, it actually says that you shouldn't use deep learning because you can never fully explain that why the decisions were as they were. But luckily, this is not applied that strongly, at least now. But also in this group is important that you can verify that you are treated fairly. So if you get suspicious that is it perhaps some gender or racial bias that affect how you are treated, you need to know that what is the features that cause this prediction. And then you have to also be able to correct data if you notice that it's wrong. And just a word of caution, this is a very hot topic. And as in this field, technologies come and go. There is this famous Gartner hype cycle that tries to model how new trends always come and how they go. So at the beginning, there is this hype phase where the expectations are like, it's loaded with expectations, how it's gonna solve all the problems and so forth. But soon when they start applying it, they notice that they are not going to meet the very high expectation, and then there is a drop of interest. So the explainable AI is at the top of the hype about like now, So if you read something about the explainable AI, always remember to read it with a critical eye, because there is a lot of unnecessary hype and promises that cannot be kept. So just the word of caution. So if you read that somebody is saying that we can see in the brains of AI, or we can make the black box transparent, or any kind of these words, it's very probably to be bullshit. So I will go through these most common methods first. So limma and SHAP. Because of this project, and also because of personal interest, I've been looking a lot of webinars on explainable AI. And in those webinars, it's very common that they say that, okay, we're going to list all the explainability methods and so forth, what you can try. And I always look into them because as a xAI researcher, I want to know that what kind of methods they find. And then I'm always a bit disappointed, because the methods that they discuss about is mostly line, SHAP, sometimes Grad-CAM, but that's often it. But these limma and SHAP are very important methods. So the idea is that you have an input image. The model predicts that it belongs to a class A. You want to understand that which pixels contributed to the prediction. And instead of looking into the model, as this is model agnostic, it doesn't need to know about anything about the model. So instead of looking into model, it starts making changes to the input image to see what is their effect to the result. And it makes these multiple tries of this, and then it can make a conclusion that these pixels affected the most. But because it's almost impossible to go through all the possible combinations, they compute different, limma and SHAP work a bit differently in the background. So limma in the background trains or approximates the prediction with this thing called surrogate model. And that's why it's a lot faster than SHAP, because it approximates the output better and quicker. But the problem is that the surrogate models are not always very good. This means that the limma can produce clever results, or sometimes it's a bit of conflict. Do the explanations make sense or not? SHAP works differently. It requires a lot more trials, so you have to compute a lot more change a lot more this input image, and then calculate the predictions. So the idea is, behind the SHAP is game theory. In game theory, there is this thing called player score. And the player score tells that if you have a team of players that compete against other team, the team either win or loses. And they want to know that which is the effect of each of the players to the outcome. A high player score means that if the player is playing in the team probably wins compared that the player is not playing. Whereas a low score means that if the player is playing in the team probably loses than if the player is not playing in the team. So it uses the same tactic, but with pixels. And that's why it has it's good, because it has a strong background from game theory. So just to list through the good and bad points of limma and SHAP. So first of all, these are very important because they are independent of the model. Also, they work with different inputs. So tabular data, images, text, so forth. It's also easy to use because there is many ready-made packages. But then as the bad sides are that they are very slow, because they make modifications to the image and then see the result. And especially SHAP is super slow. And also, if you use SHAP, remember that it underestimates the impact of correlated features, because the game theory or the player score assumes that the players are independent of each other. Then also the results are not always very convincing. So Lime is not very accurate to make these explanations. And the SHAP gives more accurate results, but it's often not good at explaining beyond the highest class. So the explanation kind of reduced very quickly. Then also Lime has these stability problems, that if you add small amount of Gaussian noise to your image so that you don't see it with human eye that it has been changed, but the explanation changed. That's why, like, combining the pros and cons, it's often that SHAP is clearly preferred compared to Lime, because SHAP is more stable, and even though it's slow, it's still like, if you need to like choose between these two models, I would suggest that you use SHAP. But then going into model-specific models. So here's the idea is the same, that you have an image and you want to know that which pixels affect to the output the most. But instead of starting making changes to the input image, you actually you look into the model. And there you first compute once the usual, first you compute the usual forward pass through the network to get the predictions. Then you compare or choose one of the classes that you want to understand or explain. And then you calculate backwards the explanations to see that which pixels actually affected most to the output. There is, because this is kind of an inverse problem, there is different ways how to sum up these weights. And there is different alternative methods how to do this. So if you have a problem, it's often good to try out different gradient-based methods to see that which one works best in your model. But this is very fast because it only requires one forward and one backward pass, and that's it. So one example of these gradient-based methods is saliency maps with vanilla gradient. So it's very simple, fast, and robust. And then it's often visualized such that there is a heat map, where hot means that there is a big impact on the model's final decision, and cold means that it has a low impact on the model's final decision. So for example, here is images of church, tractor, and manta ray, and then the explanations of these predictions. But the problem here is that it's not very class specific. So saliency maps for cat and dog are almost the same. That's why you can't really explain that why did the model see a cat in this image or a dog in this image. To solve this problem, there is Grad-CAM. And the modification is really simple. So in one part of the network, you propagate back only positive gradients. So those pixels that has a positive effect to the given class. And the reason is that sometimes positive and negative gradients kind of neutralize each other. So now they only pass through the positive ones. And now there is better distinct maps between the classes. Now it's clear to see that, okay, these are the parts of the image that resulted in cats, and these are the ones that resulted in dog. And if you want a fine-grained map, you can use this guided Grad-CAM to make very detailed explanation of your model. But with these gradient-based models, there is often this question that is it actually explaining the model or simply the inputs? So there is this one study that compared different gradient-based models and compared their results to a simple edge detector. Edge detector doesn't need a model or training data. It's very typical computer vision tactic, and the idea is to simply compare the neighboring pixels and see the brightness levels, and then it detects the borders of the image. And as you can see that these explainability methods, many of them actually resemble a lot like this edge detector. So they went further and started to change the learned weights into random weights. So they started to randomize the network layer by layer, and they noticed that some of these gradient explanations, even though the network was completely randomized, still managed to make reasonable explanations. But for example, Grad-CAM didn't work after making these random weights. And they also tested this, that what happens if they train with completely random data? Can they still make reasonable explanations? And they figured out that yes, they can. So the problem is that it seems that many of these methods actually doesn't explain anything about the model. It explains the input, and we know the input, so we don't need to be really explaining that. So this raises the question that, are these actually any good, these kind of explanations? At least I'm not a big fan of these, because you never know that is it that your model sucks, or is it that your explanation sucks, or is it that they both suck? So going forward, so looking into the training data, this is called as the pre-model explainability. So before you train a model, you actually look into the training data and try to explain it. The training data has a big impact on the final model. And there is this saying that garbage in, garbage out. And the network very easily learns from the bias of the data. So when you start a new project, it's very common that you want to see some data. So you randomly select some data from each classes to be able to compare that, okay, these kind of images are in this class, and these kind of images in this class. But the problem with this random set is that it doesn't actually tell you that which ones are typical data points and which ones are rare cases. For these reasons, there is this idea about prototypes and criticisms. So a prototype is a set of images that sufficiently well presents the data. It can be considered as typical data points, and criticisms are those ones that are not well presented by prototypes. So kind of the outliers or rare cases. And with this approach, that if you select prototypes and criticisms from the image set, the human can build a better mental model of the whole complex data space. And how this actually works, there is two different methods. The first one is the statistical. It's called the maximum mean discrepancy. I won't go into details of this. You can read them in the paper. And then there is the second one called adversarial method. And the idea in this is that you make small modification to the original image. And this modification is not random. It's optimized by the gradient approach, where the idea is to make as much impact to the to change the predictions as possible. But if you make such like multiple of such modifications, but the predicted class still stays the same, then it's considered as prototype, as like kind of like very strong case of this class. Whereas if it's very easy to change the predicted class, so it changes only one after one change, then it's considered as criticism. Here you can see the comparison of these two methods that are done for the class banana. And as you can see, the prototypes looks kind of like what you would think that the banana class look like. And in the criticisms, you have clearly rarer cases. But you can use this to understand the training data, but there is also other interesting applications. For example, you can analyze the mistakes that your model did. So when you notice that this set of images were wrongly labeled, you can use this prototype and criticism method to see that what kind of things are like typical mistakes and what are like rare mistakes. And then by looking into that, you can perhaps detect some patterns in the errors. One important thing also was that with this approach, you can actually find biases. In this paper, they looked at the prototypes and criticism of the basketball class. And they noticed that in the criticism images, 90% of the images had at least one white player, whereas in the prototype images, 78% of the images had one black player or more. So it led them to think that the data is biased. To prove, so because of the training data is biased, the model probably will be too. To prove this hypothesis, they went and downloaded similar image pairs from the internet. And as you can see, these two rows show very similar images, but the network seems to be looking at the faces of the players to detect that what is the sport that they are playing. And black people are clearly playing like basketball. But with the white people, there is more difference in the classes. The funny thing is these ping pong players, because I am not a sports person, so previously, before doing this research, I didn't know that there is this stereotype towards Chinese ping pong players, but that's actually a bias that more than one explainability method can find from the training sets. So this is like, to find these prototypes and criticisms is like very nice way to show that what are the typical and rare cases of an image change. But there is like, I would see at least a lot of different applications where you could use this. Then going forward, this is now one of the alternative methods. So this is not very widely or very well known. This is a method called testing with concept activation vectors. And the idea is to find biases in the model. For example, you could ask a question that is a concept called gender and important for a doctor score. And for this, you need images of doctors. Then you need to have a trained model, and then you will have the final score. And the idea is that you compute this TCAF score, and based on this score, you can say that yes, the gender is important for the doctor's score or no. And how this works, in the paper, they give this example that are stripes an important concept in the class zebra. The setup is that first you need to have the concept images, for example, stripes. You can use, for example, Google search to find those. The more you have of these stripe images, the better, but they said that this might work already if you have 30 images. Then you need also a random set of images. that are not used in the training and doesn't contain the zebra class. And then you need the images of zebra. Then the actual method is a bit more complicated, and I don't explain it very fully. But the idea is to select one layer from the model. Then you compute the stripe images until that layer, and also the random images until that layer. Then you try to train a linear classifier that identifies the striped images and then the random images. Then you take the zebra images. First, until the layer that you are looking at, you compute the zebra images as normal. Then in this layer, you actually push the zebra images towards to be a bit like more stripy. So you use this linear classifier to make the images to look a bit more stripy. And then you carry on calculating the remaining part of the network. Then you calculate that if the zebra class got higher values because it was made more stripy, so more than 50% of the images got a higher zebra class due to this modification, then it means that the stripes is an important concept in the zebra class. And so the results, they were able to find some common sense biases, like red is an important concept for fire engines, stripes for zebras, and Siberian husky for dog sleds. Then they also find some gender and race biases, like these ping pong players that I hadn't heard about before looking into these methods, but apparently it's a real thing. And then they find also that there is a high correlation, or the female gender is very important concept for the apron class, which kind of makes sense. And so, and also is a baby. So as a conclusion, I would say that this is a promising idea, but the results are not very ambitious. And I would say that more tests are needed to see that if it's actually a viable method or not. And then going to the last method, so counterfactual visual explanations. I would call these a bit like poor man's what if tool for images. These what if tools are very important for, or were very much wanted in tabular data. So for example, if you are applying for a loan and it gets rejected, you want to know that why, like which parts should change so that you are accepted to have a loan. And then you can get results like you need to have more savings or you have to earn more. But that's easy with the tabular data because you can use statistics to calculate that. But with images, it's more difficult. And that's why this method, I wouldn't take it too seriously, but I just want to say that there kind of exists a what if tool for images. The idea is that you have an image and then you want to change the prediction of that image. For example, you would want to this image of 3 to change into 5. Then you start making changes according to this tree structure image of 5, and start making edits to make the number 3 to look like 5. And as you can see, I would say that these results are a bit like bad copy of the structure image, and at least I wouldn't see very much the benefit of this. But then they use this also for the birds. And the idea to use the bird species is that humans are bad detecting different bird species. So could it be that AI will help them to teach that? And in this bird dataset, the dataset contains information on how the bird is oriented. That's why you can find very similar to structure image from the image sets, and then make very reasonable results. For example, in the first case, changing the head will change the prediction. And on the second example, if you put the yellow dot in, it will change the prediction. But if you don't use the orientation and you choose the destructure image randomly, then the results doesn't make any sense. So you get these monster images, and I don't think that this will teach anyone about the different bird species. So I wouldn't take this too seriously, but if there is some reason you need to have this what if tool for images, this is one that you could use. Okay, so that was all that I managed to fit into this 25-minute presentation. So as a final remarks, remember that AI models inherit and magnify the bias of the data very easily. And that's why it's also important that both the training data and your model. Explainable AI is very important, but it's badly hyped topic. And remember that explainable AI is always approximation of the full solution, and it always lacks some details. Also, don't trust blindly on one method. Try to use different methods instead. But then there is the very important thing that if you use xAI correctly, it helps us to make better and more fair models. And when I was going through these papers, I found one blog post that listed some xAI software packages that contain some of the methods that I showed in here. So if you want to take a look, there is the link to it. But many of these methods are still not very mainstream, so you can't find them in the packages. You have to do a lot of coding yourself in order to test them. So thank you from me and my home colleagues. And if you have some questions, please contact me via email or via LinkedIn. Thank you.
Thank you, Sara. That was really interesting and really insightful. So I have a few questions from the chat. Again, if you have any question, you may ask them. You may write them down in the chat section. For you, Sara, I have two questions. Okay. First, a question from Hunain, which is, can some of the methods you described be used to counter some attacks on neural networks? For example, pixel alteration.
So what kind of attacks? Can you repeat?
You may also see it in the chat section.
Okay.
Well, I'll repeat it. Can some of the methods you described be used to counter some attacks on neural networks? For example, pixel alteration. I think, if you, in some cases, I guess, about this question, in some cases, you may alter the image, for example, you may add some noise or something that may cause the model to make a different prediction.
There is methods that can do that. So you can make attacks to the network by calculating the most effective way to inject the network and change its prediction. But if you think it's vice versa, it's a lot more difficult to find these kind of attacks. So I haven't found that kind of explainable AI methods that could find that now these images are tried to be attacked with some method.
Okay. So another question, again from Honain. Do you think that more explainable AI methods should be used to fix models and remove their biases, or rather inform us about our own biases?
Well, I guess it's a longer question, but yeah. So I think the idea is to try to fix the models and remove the biases. But to inform us about our own biases, it's a bit more difficult because the majority of the training data is collected from white, rich countries. So that's why the data sets are often already biased. And then there is a lot of problems that, for example, if you collected the data kind of like wrongly, so many collect them, like, for example, using news articles. There, for example, Black people as criminals are sampled very high, and often Black people are not presented as in a good light. So that's why how you collect the data is actually more important than what kind of biases the people might have, I would say.
Okay, yeah, thanks. I think that's all the questions there is at the moment. But thanks, Sara. Now we go to the second talk with Aapo Tanskanen. You may share your screen, Aapo, now.
Yeah, thank you. Hello. Let me share my screen. Okay, now you should see some slides. So,
yes, we do.
Yeah, hello everybody. I'm Aapo Tanskanen from Gofore. I work there as a data scientist. I've been working there now a little bit over 2 years, and well, I've been doing quite many different projects, anything from basic data analytics to more advanced, like machine learning methods to predict electricity consumption and so on. Also, I've been working with chatbots and this natural language processing projects. And yeah, I would say natural language processing, or NLP in short, has been my special interest a few years now, and especially these very latest transformer-based models, which are like every new models and papers are coming up almost every week or month, and so it's quite interesting field to be working with. And yeah, that's why I'm going to present for you today about zero-shot text classification without GPT-3. Yes, you don't need GPT-3 for every single thing in the world. You can manage without it quite nicely. And yeah, I will show you first the agenda of my presentation. So I have 3 points. At first, I will give you a brief introduction to the zero-shot text classification and try to explain what does it mean and how does it work. And then next, I will go briefly through some like pros and cons of zero-shot text classification compared to the more, let's say, traditional way of fine-tuning your own NLP classifier. And lastly, if we still have time, I will show you some quick live demos of zero-shot text classification. And yeah, if you have questions, please just write them down and I will answer them later at the end of the presentation. All right. So yeah, at first I could clarify a couple topics in the context of my presentation. So when I'm talking about zero-shot, I'm meaning like, okay, zero-shot learning might be a familiar topic for you from some other data science task, like from computer vision or somewhere. But in the context of this presentation and in NLP, by zero-shot, I'm meaning that we are trying to get some NLP model to do something else it wasn't actually explicitly trained for originally. So that's the xerosot part. And when I'm talking about NLP models, I'm referring to the transformer-based language models, for example, Google's BERT or GPT-3 or BORT or whatever. We have so many different models nowadays. So I'm talking about those latest models. And yeah, and then if you are working, especially in the business side, for example, I'm working with some like companies and they have some problem. Okay, we want to classify some text, but there usually are some problems with the data. They might not even have any data which you could use to train your supervised text classifier. Or if they have data, it's usually not labeled. So you need to use a lot of time and resources to label the data. So there are these common problems with access to good enough quality labeled datasets. Usually what you need to train your own text classifier in the traditional, so-called traditional way. So that's like interesting challenge that could we actually use some other NLP models trained for some other common task already available to do the text classification in my specific text classification problem or task. So that's the xerosot classification. Could we get some NLP model to do the classification for us, even though we don't have data to train our own classifier? Short answer, yes, we can. The headline is it's already telling little secret about it, how it's going to happen. But at first, I'm going to give you a brief introduction to NLE task, which we are going to use to do the xerosot text classification. So NLE is a short version of natural language inference, and natural language inference is one of the most common NLP tasks or problems, especially in the research side. So because it's so common task and we have a lot of like benchmark data sets for that task and so on. So we have a lot of different available good quality labeled data sets for the NLE problem. And also we have a lot of already pre-trained or fine-tuned NLP models available for free to use. So we could use those resources available to do the xerosot text classification. And if you are not familiar with the NLE task, I'm trying to give you a short introduction what does it actually mean or what we are going to do with the NLE. So the NLE is actually a task of determining whether some hypothesis is true, false, or undetermined given some premise. So basically the NLE model is it's like hypothesis testing task or model. So the model is trying to like predict whether a hypothesis entails a premise or does it contradict with the premise or is it like neutral to the premise. In practice, this is a sequence pair classification task. So we have hypothesis and we have a premise, two different texts, and those both are fed together through the model, and the model tries to predict one class of either entailment, contradiction, or neutral. And here I have two examples. So if we have a premise of a group of data scientists are listening to a presentation about NLP, like we are right now doing. And then we have a hypothesis. Okay, some people are playing football. Human could say that hypothesis is false. It contradicts the premise. And so the model should also predict the contradiction class. But if we have the same premise again, but we change the hypothesis into some people are participating in technology presentation, the model should predict a class of entailment. So it's actually true. The hypothesis should be true. So this is like how the NLE task works and how those NLE models are working. So it's basically a hypothesis testing kind of task. Next slide, I will try to explain how can we now turn the normal text classification task into NLE task, so we can use those available NLE models to do the zero-shot text classification. So this idea of using NLE models for zero-shot text classification was originally proposed by Yin et al. At the last slide, I have some links for you to read if you want later on for the paper and some blog posts. So the idea, what the Yin et al. Proposed was that, okay, we could use the premise. We could use the text we want to classify as the premise, and then we might have some candidate labels, what the text might be about, and we will use those labels as a hypothesis. How we are going to do that is that we need to formulate those candidate labels into some kind of hypothesis format. So usually there are many different ways you can do that, and some ways works better for some specific text classification problems and some for some others. But some like common general way is in this second sub bullet here. So we can formulate the hypothesis as his text is about some candidate label. And so the NLE model then tries to predict whether this hypothesis is true, false, or neutral. And if the NLE model predicts the class of true, so the entailment class, we will assume that, okay, it's true, and this candidate label is true. So the text is about that label. One more point about the hypothesis format. So as you can see, the format, this text is about something, it mimics how humans would do the text classification. So we are actually like mimicking how humans would do the classification. So for example, if I'm reading some news article and then some person comes and ask from me, okay, hey, can you tell me what is the topic of that news article? And then in my mind, I could like make this hypothesis. Okay, I think this text is about politics. So we are actually trying to mimic that human way of classifying with the NLE models. I have a little example here. So again, we have the same premise as previously. A group of data scientists are listening presentation about NLP, and our task is to classify whether this text is about technology or not. So we can formulate the hypothesis as his text is about technology, and then the NLE model could predict the class of entailment true. So this text is about technology. But that was only like one class, but what if we have a multiple candidate labels? For example, for the news articles, we could have many different possible news topics. So how can we classify that with the NLE model? And we can do it by feeding every single candidate label separately through the model. And then at the end, we take the entailment dimension of the output, take the logits, and then we like do the softmax over that. So we can get scores for all labels and see which label gets the highest probability. So here again, I have a real life example of again the same premise. A group of data scientists are listening in presentation about NLP, and then we have some candidate labels. Okay, this text could be about technology, it could be about sports, or could it be about politics, or could it be about economy? And then we will feed those candidate labels through the model and get the at the end do the softmax and get the scores for every label together. And here it's a real example what I have those scores here. I did it previously, and so the technology gets like 95 probability, and economy, sports, and politics are like almost 0. So that seems to be working quite well. And yeah, that's the basic idea how can we use NLE models to do zero-shot text classification. That's I think it's kind of nice idea. How can we like mimic the human way of classifying text with these neural networks and NLP models? Yeah, then finally some pros and cons comparing to the more, let's say, traditional way of fine-tuning your own supervised classifier. And by that I mean with this latest transformer-based NLP models, you usually take some large pre-trained language model, and then you have, let's say, some much smaller labeled dataset for some classification task, and then you like fine-tune the pre-trained model for that classification task. So that's the, let's say, traditional way of using these latest state-of-the-art NLP models to do the classification. So if we compare that to the zero-shot way, of course, the big pro of zero-shot classification is that you actually don't need any labeled datasets for training your own classifier, and you don't need to use resources for training the classifier. So you can, especially for, let's say, proof of concept projects, if you want to just like, you have an idea, okay, maybe in this problem I could need text classification, part of some bigger system. I could just quickly try out, okay, does it work or not in my case? And I can just take a NLE model and try the zero-shot text classification and see does it work or not. And if it gives me good examples, then I could maybe use some resources to actually get the labeled dataset and train my better model for that. So it's quite nice because you can immediately straight away get results with the NLE models. And yeah, but with the supervised classification, you need to always like train your specific classifier, and you need to have good enough labeled dataset, and yeah, so you need more resources for that. And another big pro of zero-shot text classification is that you can actually use the same NLE model for multiple different domains and labels if that model has been originally trained with good quality dataset which has like text examples from different domains and labels and so on. So you can use it, for example, to classify news articles or classified sentiment of some text or almost anything. But with supervised methods, you can only predict classes introduced in the training dataset. So it's more limited in that sense. But then a negative thing about zero-shot text classification is that if you are going to use that model in a production, so we call it inference. So the inference speed, it's usually slower or much slower than the supervised classifier, especially if you have many candidate labels, because you need, with the zero-shot models, you need to always feed through each and every candidate label separately through the model, so it takes more time to get the end result with the zero-shot models. But with supervised classifier, you can only feed through the text to be classified once, and you will get the result straight away. So the inference speed should be much quicker. Also, another negative thing about the zero-shot text classification is that, of course, you cannot expect as good accuracy as with the supervised methods, because the NLE model wasn't trained with your very specific data, so of course you cannot expect as good accuracy as with the supervised methods. But I've been testing those zero-shot models a little bit, and I think for some common text classification tasks, you can actually get quite nice and maybe good enough results with the zero-shot method. So it still has a lot of different use cases. And yeah, one final negative thing about the zero-shot method is that each candidate label you may have need to be able to be formulated as a natural language hypothesis. So again, the human way to classify text. So for example, if you have some business case that you need to classify this text into number 1 and this text into number 2 and another text into number 3, you cannot do that with the zero-shot way, because if you formulate the hypothesis again in the format of this text is about something, and then you have candidate labels of numbers, and you have for example, hypothesis, this text is about 1, and the text you want to classify is something business related stuff, so it cannot actually know that is it about number 1 or not. So those labels you need to be formulated as a natural language hypothesis. So that might be a limiting thing in some cases. But yeah, I think we still have time for demos, so I could now switch on to the demo section. Yeah, wait a minute, I'm trying. Okay, yeah. So yeah, you should now see my Colab, Google Colab. You may be familiar with the Colab, so it's basically a Jupyter notebook in the cloud offered by Google, and you can get GPUs for free, but actually I'm now using only GPUs at the Colab. But yeah, if you have been working with NLP stuff, and especially with these latest transformer-based models, you may be familiar with the Hugging Face and Hugging Face transformers. So I'm using that library here. And it's really nice library for many transformer NLP tasks. And again, I also have this another library from Hugging Face called datasets, which you can use to load many different datasets. But actually in this demo, I'm not using that, but just quick hint, you can use this to load many common datasets for training your own models or testing your own models if you want. After that, we just import the pipelines from transformers. So transformers, if you want to, for example, demo some stuff, they offer these quick pipelines for doing the common stuff quickly without coding too much by yourself. But if you want to maybe go into production, you may want to do some other stuff by yourself. So then we just load this zero-shot classifier model with the pipeline. So we, at the zero-shot classification here, we want to load that kind of pipeline. And then we are defining a model. And now I'm using this model called BARD, large MNLI. So this BARD model is from Facebook, and it's a large variant of that. And that model has been fine-tuned for this NLE task. So that's why here we have this NLE part at the end. But you can also, here's a link for the Hugging Face models repository, so you can see some other available fine-tuned NLE models from there for the zero-shot text classification problem. And yeah, then I just copied, maybe was it last week or so, I went to the Yle, this Finnish national broadcasting company, to Yle's news website, and I searched for English news for there, and I just copied few text for demo purposes here. So this first text is news article about, I don't know if you can see, but it's about some football, Finnish football stuff. So it should be about sports news. And then we have the second text, which is about some Finnish politics, about like this prime minister and her party stuff. So it's like politics news. And then I added some candidate labels into the list. So we have sports, economy, politics, and culture. So we could try to classify those two news articles into one of those possible candidate labels. And then we just, with this Hugging-based pipeline, we only give the text we want to classify and then the candidate labels, and then we can formulate some kind of hypothesis. And here I'm just using this quite common formula of this text is about, and then we add the candidate label at the end. So if we now run it, let's see if it works or do we get some demo effects. It might take a few seconds to load because actually the news article is quite long article and we have 4 different candidate labels. So as I said, the xAI text classification is a bit slower than the more traditional supervised classification methods, especially with the GPUs. When we are using these large transformer models, those are quite slow with GPUs usually. So here we get the results, and as we can see, we have sports as a number 1 label, and it has the probability of 57%. So we could say the xAI classifier was able to classify it correctly because it was about some Finnish football stuff. Then if we do the second classification, so now we have the article about some Finnish politics stuff. So let's see, do we get the politics as a number 1 class? And yes, we do. So again, we have the politics as a number 1 class, and again the score is about like 58. So not so high, but still quite a bit higher than the other labels we had in the candidate label list. So I think the model was again able to classify text quite nice. But then my mouse is lagging a little bit, but okay, now it should work. My last demo part is that, okay, we can actually use, as I said in the pros of xAI way, we can actually use the same NLE model for different domains and different classification tasks and with different labels. So now those first 2 examples were like topic classifications, but now we switch to sentiment analysis or sentiment classification. So I here just typed this so-called movie review about the movie Tenet, and it says that, okay, the movie was really great, but maybe it was a bit long, so some negativity at the end of the text. And I gave it the candidate labels of positive and negative. And again, the same hypothesis, this text is about something. And now I just before click the run button, and we can see the results of positive being 63 and negative 36. So we could say, okay, the same NLE model also works for sentiment classification, at least with this quick demo. But one last part of my demo, I could show you that actually with these NLE models or this xAI way of classifying with the NLE models, it might be beneficial to actually a little bit like try out different kind of hypothesis templates. So we can, one common way of actually introduced in the paper I mentioned earlier, in the paper they used a little bit different hypothesis template for sentiment classification, and it was actually like in the format of this text expresses. Now we have that. So now it's more like human way again. We are having this template that this text expresses some kind of emotion or sentiment. So now when we run it again with that hypothesis template, we can see that, okay, the positive got a little bit higher score than previously. So the model is maybe more confident that, okay, it's actually positive movie review, which in my mind, it still is positive movie review. So yeah, you may need to like try out different hypothesis templates to get better results with the zero-shot text classification. And in that sense, it a little bit resembles the GPT-3 hype that you need to like be like prompt engineer and do some prompt engineering. So now we are doing hypothesis engineering. We try to like get the best results with some specific hypothesis template at your specific text classification problem. Yeah, that was my presentation. I'll just show the last slide. So here you can see the link to the paper. I can actually maybe add those links to the chat too, so you can open them better. But yeah, link to the paper and also link to one blog post about zero-shot text classification. And yeah, you can contact me at LinkedIn or now, or send me email at my first name, last name at go4.com. And yeah, thank you for inviting me to speak. And if you have any questions, I'm now free to ask.
Thanks, Aapo. Thank you very much. That was really interesting and very insightful. And about the last classification example about Tenet, it's also hard for humans too. So
yeah, I know.
Yeah, so I have a few questions from the participants. One from Mia Le. I read it out. So if I understand correctly, we can only use the pipeline if the transformer model has already been fine-tuned to perform this task. So I would love to try zero-shot classification on Swedish text. Do you think maybe I can fine-tune a Swedish BERT on this classification task? Please correct me if I'm wrong. And thank you.
Yeah, that's good. That's a good question. So the model I used in the demo, it was already fine-tuned for the NLE stuff, NLE task, and it was fine-tuned with English dataset. And the pre-trained language model, Facebook's Bard, it was also English model, so it only supports English text. But actually, if you go to the Hugging Face model repository, you can already find some multilingual models fine-tuned for the NLE task. So you can use those models to do multilingual zero-shot text classification. And there are also models, for example, also from Facebook model called XLM Roberta or XLMR for short. That's a multilingual model. It supports like 100 different languages, Swedish include. I'm quite confident because Finnish is also supported by that model. So Swedish should be supported too. And those models already have been fine-tuned for the NLE task too. So you can use that to zero-shot classify some Swedish text. But you can also try out your fine-tuning your own NLE classifier and then use that for the zero-shot classification. And I have been also doing that or experimenting with that. I don't have any Finnish or Swedish. I don't know if there are Swedish NLE datasets available, but if there are, you can actually take the pre-trained Swedish BERT model and fine-tune that for the NLE problem with the Swedish NLE dataset, but I don't know if there are available Swedish NLE tasks. But anyway, you can try out that also by yourself if you want. I've been trying that and it's quite easy if you just have the available NLE data.
That is one. That is a good question, and Well, I have also one question of my own, maybe a little bit related to this. In your demo, I saw that you chose to implement like BART, BART NLE, if I saw it correctly. Is that a preference, or like why did you choose exactly that one over, for example, BERT, or was it just for the demo?
Yeah, it was just for the demo because how could I explain it shortly? Well, that BART model has been like favored model for the Cherosot classification by Hugging Face people, so that's why I use it. And if you search those NLE models for Cherosot text classification problem in the Hugging Face repository, you can see there are maybe less than 10 models available already, so not so many, but I'm not sure if they had any BERT model, or how do you pronounce BERT, but I think they have BART and the XLMR, which is the multilingual version. But actually you could use, there are many NLE models in the Hugging Face repository, but the Hugging Face Cherosot classification pipeline requires some modifications to that model's config file, and so that's why you cannot use those other NLE models, which I'm sure there are some NLE models trained with or fine-tuned with the BERT model, but they have a little bit different config file, so you need to modify that before you can load it with the pipeline. So that's why you cannot out of the box use those, but it's quite easy modification. You just need to like change few lines. I can tell you more about it later if you want. But yeah.
Thanks. I have another question from Radim. Are there any issues with more exotic languages such as Finnish? For example, being less accurate in predictions comparing to English? That is a question. So he's asking, I think it goes same as the first question. He's asking about the accuracy of Finnish compared to English.
Yeah, I would say it's you cannot maybe expect as good accuracy as with English or more common languages. It's common problem with the NLP stuff because we don't have so many data sets and models for Finnish or more not so common languages. But with the multilingual model, the XLMR, which I mentioned earlier, you can actually get quite nice, I think, at least for some common classification problems, quite nice results also in Finnish text. I have been myself trying to fine-tune my own multilingual NLE model for Cherosot task, but the problem is that you don't have NLE datasets in Finnish, at least not yet, but you have like some multilingual NLE models which have datasets which include like maybe 10 different languages, but not Finnish. But if you have use the multilingual, for example, the XLMR pre-trained model as the base model, which already supports 100 different languages and has been trained with Finnish data. But if you take that and fine-tune that with your own more specific NLE datasets containing, let's say, 10 different languages, but not Finnish, the fun part is that actually the model still supports Finnish, but maybe not as good as if you would have had some Finnish NLE examples in the dataset. But yeah, you can try it out. It can work, and I think it works in some cases. I think if I remember correctly, I tried with one of my own like Finnish news topic classification test sets, and I think with like training the traditional supervised classifier with that and using that test set, I was able to get like, let's say, over 90% accuracy, and with training the multilingual Cherosot NLE classifier, I was able to get maybe something like 75 or around that level of accuracy. So not as high as the traditional way, but still like quite nice.
Thanks. Thank you very much. So I guess that's it. No more questions for you. And
no problem. Thank you.
Yeah, thank you again, Aapo. Thank you, Sara. Thank you, everyone, for participating. And hope you enjoyed the event. Thank you, and see you on the next month.
Thank you to everybody listening, and thank you also for Aapo to giving a great presentation.
Thank you, you too.